This lecture is brought to you by Megger, a leading manufacturer of electrical test and measurement equipment. I've trusted Megger's equipment for years and have witnessed firsthand their commitment to education and supporting technical schools across the country. For a limited time, Megger is offering my viewers an exclusive discount on their next purchase on products sold through U.S. distributors. Simply visit us.megger.com/bigbadtech for all the details. Good day and welcome to Big Bad Tech. I'm your instructor Jim Pytel, and today's topic of discussion is Thevenin's theorem as applied to DC circuits. Our objective is to learn to employ Thevenin's theorem in an effort to simplify complicated linear two-terminal networks into their Thevenin's equivalent circuits. Ideally, the original and the Thevenin's equivalent circuit will behave identical to each other. However, the Thevenin's equivalent circuit will be notably easier to build and to solve for desired electrical quantities. Bottom line up front. Thevenin's theorem is essential to your progressive development in the basic electronics series. It is a key rite of passage and will be regularly employed because it has the power to render even the most tangled and gnarly of series parallel circuits into tame and docile pure series circuits that sit, stay, and roll over on command. I will admit Thevenin's theorem is not exactly the easiest theorem to learn because it requires a degree of spatial awareness that may or may not be your strong point. In my experience, individuals struggling with Thevenin's theorem don't necessarily have issues with the electrical concepts, but rather they have issues visualizing a circuit from different perspectives. It is for this reason I typically start discussions on Thevenin's theorem with this seemingly simple question. What is the resistance of this 4-resistor circuit? Before you rush to judgment, be warned, I've given you no solid ground upon which to stand. Resistance is a two-point measurement. Which two terminals are we reading resistance from? If we read resistance from A to D, R2, R3, and R4 are clearly in series with one another, and this series path is in parallel with R1 for a total resistance of 153.4 ohms. If, however, we read resistance from B to C, R2, R1, and R4 are clearly in series with one another, and this series path is in parallel with R3 for a total resistance of 240.7 ohms. If we shift our terminals of interest yet again, from B to D, now R1 and R2 are in series with one another, as are R3 and R4, and these two series paths are in parallel with one another for a total resistance of 275.4 ohms. Numerous other combinations exist, each with its own total resistance value. The point is, resistance measurements of this seemingly simple circuit are like trying to nail jello to a tree if you consider different perspectives. This is the biggest stumbling block I've witnessed for students first learning Thevenin's theorem, and I'm asking you to keep this in mind when putting it to use. Observed electrical properties depend upon your perspective, and Thevenin's theorem shifts perspective from the source to the electrical load and back again. Throughout the course of the DC circuit analysis playlist, you'll notice that I've regularly drawn sources on the left and electrical loads on the right, only very rarely switching it up now and then. This isn't a necessary requirement, and the only reason I've regularly made use of this convention is out of sheer pity for those enrolled in basic electronics classes. Trust me, I've been there, and I was just as confused and frustrated as you when I first learned this material, back when the wild mullet still roamed the earth. My biggest complaint about textbooks isn't that they're expensive, heavy, static, poorly written, and hopelessly old school. It's that the example problems accompanying each chapter are so awfully convoluted and impractical that students just learning electrical properties are so shaken by the purposely goofy obfuscations they never learn the electrical theory the practice problem was intended to demonstrate. Hamlet doesn't just start out with some dude getting stabbed. A better approach might be to start easy and slowly turn up the heat. Not sure if you've noticed it or not, but if you've been following this lecture series in its intended order, I've been progressively turning up the heat. Sure, the illustrated example problems include general guidance, but think about it. I'm not holding your hand leading you through every step of a calculation, telling you which numbers to punch into your calculator, nor reminding you about engineering notation anymore. I say things like Ohm's law states this, and because this is in series with that, we can assume this, and so on, and just flash a number on the screen and move on. Not sure if you've ever looked down, but I pushed you out of the nest a long time ago. If you've reached this point in this series, it's because you're still flying. Let's turn the heat up another notch. See if you can solve for the voltage across, the current through, and the power dissipated by the variable load resistor R load when R load is set to 500 ohms for these 4 circuits. Again, we're only looking for the voltage across and the current through R load for each of these 4 circuits when R load is set to 500 ohms. By all means, pause the lecture and try this on your own. Do not sit there and wait me to guide you through this exercise. perform a Kirchhoff's current law and a Kirchhoff's voltage law analysis on these 4 circuits, and determine the voltage across and the current through and the power dissipated by the variable load resistor when R load equals 500 ohms. Yes, these circuits look a little different than the ones I normally give you. Don't panic. Trust the skills you have and put these skills to the test. If you're tracking, you should have obtained the following results. Those with a degree of spatial awareness should have realized that these were not 4 different circuits, but rather 4 different iterations of the same circuit. They were all purposely goofy obfuscations of a series parallel circuit in which a source, E, sees a 440 ohm resistor in series with a parallel combination of a 680 ohm resistor and R load presently set at 500 ohms. Let's use this particular configuration for the purposes of analyses, where a 30 volt source E sees R1, a 440 ohm resistor, in series with a parallel combination of R2, a 680 ohm resistor, and R load currently set at 500 ohms. An application of Kirchhoff's current law demonstrates that source current must flow through R1, then splits into 2 paths, one afforded through R2 and the other through R load. For all 4 implementations, it can be said that I source equals I1, which equals I2 plus I load. An application of Kirchhoff's voltage law for this loop in red demonstrates that E equals V1 plus V2. Similarly, another application of Kirchhoff's voltage law for this loop in orange demonstrates that E equals V1 plus V load. Finally, another application of Kirchhoff's voltage law for this loop in yellow demonstrates that V2 equals V load. These analyses imply that R2 is perfectly in parallel with R load, a simplification I'm calling R single prime, where R single prime has a value of 288.1 ohms. R single prime is perfectly in series with R1. An application of Kirchhoff's current law to the pure series simplification demonstrates that I source equals I1, which equals I single prime. An application of Kirchhoff's voltage law for the pure series simplification demonstrates that E equals V1 plus V double prime. An application of the voltage divider rule, solving for unknown voltage V single prime, demonstrates that V single prime is 11.9 volts. R single prime is a parallel combination of R2 and R load. Voltage across elements in parallel is the same. This implies that the voltage across the load is 11.9 volts. An application of Ohm's law demonstrates that I load equals 23.7 milliamperes. Finally, an application of the power equation demonstrates the power dissipated by the load is 281.9 milliwatts. Done. As these examples were intended to illustrate, in addition to a thorough understanding of Ohm's law, one must possess a degree of spatial awareness to consider oneself adept at circuit analysis. This is to suggest that circuit analysis, despite being rooted in math and science, is not just a technical discipline, but also an art form, and that the finer points cannot be taught, but only learned by oneself. I cannot teach you flexibility, visualization, and spatial awareness. You must teach you these skills. This being said, here's some reliable tools that will help you out. Kirchhoff's voltage law and Kirchhoff's current law. Never, ever attempt to analyze a circuit without first having performed a thorough Kirchhoff's voltage law and Kirchhoff's current law analysis. Application of fundamental series and parallel properties can assist you in visualizing how current flows through and how voltage is apportioned in a particular circuit, and allow powerful simplifications to be made. Rigid and recalcitrant individuals that refuse to use these techniques break apart. You cannot be reliant upon clear programmatic instructions because there are limitless possible configurations of circuits that can go wrong in limitless fashions. Now that we had a quick demonstration and discussion about visualization, let's dive into a discussion about electrical loads. Very often circuits are designed to deliver power to a variable load resistor, often designated R load, in this case presently set at 500 ohms. Oh crap. I've discovered an error in my illustrated example problems. R load was meant to be a 200 ohm resistor. Sorry about that. Pause the lecture and recalculate all the values. Don't skip this step because it's vitally important to our later discussion. If you're tracking, you should obtain the following values when R load is set to 200 ohms. Wait a second, did I say 200 ohms? I meant R load was supposed to be an 800 ohm resistor. Sorry about that. Pause the lecture and recalculate the values. Again, don't skip this step because it's vitally important to our later discussion. If you're tracking, you should obtain the following values when R load is set to 800 ohms. Whoa, I do not know what is going on today. I am totally hosing up this lecture. R load isn't supposed to be 800 ohms. I meant R load is supposed to be 880 ohms. You can see the mistake, can't you? Go off and calculate these values again. While you're at it, calculate these same values when R load is 8.8 ohms, 88 ohms, and 8,800 ohms. I'll wait for you. A long, long time. Do you see the point I'm driving at? Every time R load changes, you change the whole circuit, and it necessitates another complete series parallel circuit analysis. This is a serious drag, and there has got to be a better way. The better way is with Thevenin's theorem. Thevenin's theorem is a two-step procedure that simplifies a complicated circuit into a single voltage source in series with a single resistance. The original complicated circuit and the Thevenin's equivalent should ideally behave the same, and importantly, the load resistor will be none the wiser to the substitution. Of note is not only the substantial ease with which calculations can be made using the Thevenin's equivalent circuit, after all, it's just a pure series circuit, but also how much less components, connections, and confusion is involved in the physical construction of the Thevenin's equivalent circuit. Which would you rather be responsible for? A complicated series parallel circuit or a simple pure series circuit with only two elements? I know which one I'd prefer. The two steps in Thevenin's theorem make use of a shift in perspective from the source to the load. Thus far, we've been performing circuit analysis as if the source is the one that's controlling the show. However, the source is really only part of the picture. Ohm's law supports this duality. Voltage influences current directly. Increase the voltage and current increases. Decrease the voltage and current decreases. Resistance, in contrast, influences current inversely. Decrease the resistance and current increases. Increase the resistance and current decreases. Both partners are necessary for the dance. Thevenin's theorem takes advantage of this half of the equation. How does a variable load resistor see the rest of the circuit? The Thevenin's equivalent circuit seen by a load resistor consists of a single voltage source called ETH in series with a single resistor, RTH. These two components are hooked to the nodes A and B, supplying the load resistor R load. To simplify a complicated circuit to its Thevenin's equivalent, we need to solve for these quantities, ETH and RTH, using two separate steps. Before we even begin discussing procedures, let me make something absolutely clear. It's all about perspective, and sometimes shifts in perspective mean different things. You can solve for ETH or RTH first. Order doesn't matter. However, you simply must understand ETH and RTH have nothing to do with each other and are never, ever used to solve for each other. Only in the Thevenin's equivalent circuit do they come together to create a pure series circuit, which should ideally behave identical to the original more complicated series parallel circuit, with a notable advantage of being easier to build and analyze. Let's start by discussing the procedure necessary to solve for ETH, the Thevenin's equivalent voltage. First, one must remove the load resistor from the nodes of interest. Next, one determines the open circuit voltage seen across the two nodes of interest. In our original example, we designated our load as our resistor of interest between nodes A and B. As previously discussed, any change in R load would necessitate a complete series parallel circuit analysis to solve for the circuit's response to the changed load resistance. Let's determine the Thevenin's equivalent voltage seen by this load resistor. Step 1. Remove the load resistor from the nodes of interest. Step 2. Determine the open circuit voltage seen across the two nodes of interest. In this case, the open circuit voltage across the terminals A and B would be the voltage across R2. Again, R load has been removed from consideration. The simplest of series circuit properties can be used to solve for the voltage across the A and B terminals for this modified circuit. An application of the voltage divider rule demonstrates that V2 is 18.2 volts. This is the Thevenin's equivalent voltage, ETH. Now that we've obtained the Thevenin's equivalent voltage, ETH, set it aside and move on to RTH, the Thevenin's equivalent resistance. Again, RTH and ETH have nothing to do with each other until the very last step. Set ETH down and do not pick it up again until we're done. To solve for RTH also necessitates a multi-step process. First, one must remove the load resistor from the nodes of interest. Next, one removes the source or sources from consideration. One removes a voltage source by replacing it with a short circuit. One removes a current source by replacing it with an open circuit. Make note that incorporating shorts and opens inside your original circuit may fundamentally change the nature of your circuit, as we'll see in a moment. Finally, one reads the resistance of the modified circuit at the nodes of interest. This, in my experience, is one of the hardest shifts for individuals to make. RTH is not the resistance seen by the original source. RTH is the resistance seen by the load resistor when the source has been removed from consideration. Again, make note that shifting perspective within your original circuit may fundamentally change the nature of the circuit, as we'll see in a moment. In this example, we've designated this resistor as our load resistor. As previously discussed, any change in our load would necessitate a complete series parallel circuit analysis to solve for the desired quantities. Let's determine the Thevenin's equivalent resistance seen by this load resistor. Step 1. Remove the load resistor from the nodes of interest. Step 2. Remove the source or sources from consideration. In this case, it's a single voltage source, necessitating it be replaced with a short circuit or 0 ohm resistor. Finally, one reads the resistance of the modified circuit at the terminals of interest. If you want to, you can draw a little ohm meter on the terminals of interest, reminding you that perspective has shifted. The removal of the source and perspective shift changes the game, and a lot of people unnecessarily freak out about this. Chill out, relax, visualize the circuit at the nodal level and from the perspective of flowing current. In this circuit, an ohm meter reading the resistance from A to B would see R1 clearly in parallel with R2. This is fundamentally different than the relationship we previously observed when calculating the open circuit voltage ETH and during the original series parallel circuit. That's the point. There's been a shift in perspective, and calculating RTH has nothing to do with ETH. R1 in parallel with R2 is a 267.1 ohm resistor, meaning Thevenin's equivalent resistance, RTH, is 267.1 ohms. Now that we've obtained the Thevenin's equivalent resistance, RTH, let's set it aside and take a break to discuss what just happened. Again, solving for RTH and ETH had nothing to do with each other. There's an impenetrable brick wall between them, and they can be solved for in the order of your choosing. ETH and RTH only come together in the final step. On a practical level, if one was to really physically build the original circuit, one could experimentally determine the Thevenin's equivalent voltage and resistance using identical techniques. One would experimentally observe ETH in the following fashion. First, one would remove the load resistor from the nodes of interest. Next, one would simply measure the open circuit voltage seen across the two nodes of interest using a voltmeter. A voltmeter in this position will read 18.2 volts. To experimentally observe RTH, first one must remove the load resistor from the nodes of interest. Next, one would remove the source or sources from consideration. One removes a voltage source by replacing with a short. Note, do not short out a real voltage source. This is a surefire way to get stuck in the iron chair position for the rest of your academic career. Remove the voltage source first. Replace the terminals formerly occupied by the voltage source with a short or 0 ohm resistor. Finally, one would read the resistance of the modified circuit at the terminals of interest. An ohm meter in this position would see R1 in parallel with R2 for a value of 267.1 ohms. Whether you calculated the Thevenin's equivalent voltage and resistance or experimentally determined them, the Thevenin's equivalent circuit for this original circuit is a series combination of ETH, an 18.2 volt source, and RTH, a 267.1 ohm resistor, supplying a variable load resistor, R load, attached to the nodes of interest. If everything I've been telling you is true, the Thevenin's equivalent circuit should behave exactly the same as the original circuit, and the variable load resistor should be none the wiser to the substitution. Let's see if this is the case. Our original series parallel circuit had a 500 ohm resistor in the R load position. Then I had you swap it out with a 200 ohm resistor. Then I had you swap it out with an 800 ohm. Then I had you swap out again with an 880 ohm. Then I had to perform analysis for an R load was 8.8 ohms, 88 ohms, and 8.8 kiloohms. If you're driven enough to actually follow through with all those separate series parallel circuit analyses, you're far more disciplined than most people because each change in R load would have necessitated an entirely separate series parallel circuit analysis. You'll recall the original series parallel circuit necessitated we first take R2 in parallel with R load, a simplification we called R single prime. Then we determined V single prime using the voltage divider rule, made use of parallel circuit properties to determine V load, then Ohm's law to determine I load. Each change in R load necessitated we perform the same tedious series parallel circuit analysis anew. Using the pure series Thevenin's equivalent circuit, however, makes our job much easier. For example, if R load is set to 500 ohms, a quick application of the voltage divider rule demonstrates V load to be 11.9 volts, exactly what we obtained using the original series parallel circuit, albeit with significantly less blood, sweat, and tears. An application of Ohm's law in the power equation similarly confirms I load to be 23.7 milliamperes and P load to be 281.9 milliwatts when R load is set to 500 ohms, thereby proving that R load is none the wiser to the substitution of the Thevenin's equivalent circuit in place of the original series parallel circuit. Of note, the Thevenin's equivalent circuit is much simpler, being a pure series circuit. If we needed to perform the same analyses for a range of R load values, the Thevenin's equivalent circuit would yield faster results. For our extended range of load resistor values, 200 ohms, 800 ohms, 880 ohms, 8.8 ohms, 88 ohms, and 8.8 kiloohms, we obtain the following results in accordance with those values obtained using the original series parallel circuit, albeit with much less toil. In summary, the Thevenin's equivalent circuit yields the same results with less work. If there's one thing I don't want is more work, and neither should you. I suggest you get to know Thevenin's theorem. Alright, this concludes the theoretical portion of this lecture. Is that it? No. Thevenin's theorem is far from over. Really, the only way of understanding Thevenin's theorem is by doing Thevenin's theorem. In this spirit, stay tuned because I've got another complete lecture coming your way real soon featuring nothing but applications of Thevenin's theorem. Believe me, you'll get plenty of practice. Lastly, I need to remind you that Thevenin's theorem is an essential rite of passage in your development as an electrical engineering technician and will become a necessary and frequently employed tool. Later theorems like the maximum power transfer theorem, and to a lesser degree Norton's theorem, are predicated upon your understanding of Thevenin's theorem. In conclusion, we learned to employ Thevenin's theorem in an effort to simplify a complicated series parallel linear two-terminal network. Ideally, the original and Thevenin's equivalent circuit will behave identical to each other. However, the Thevenin's equivalent circuit will be notably easier to build and to solve for desired electrical quantities. Remember to review these concepts as often as you need to really drive it home. Imagine how well lab will go if you know what you're doing. Thank you very much for your attention and interest, and we'll see you again during the next lecture of our series. Remember to tell your lazy lab partner about this resource, and be sure to check out the Big Bad Tech channel for additional resources and updates.